We've been talking about medical imaging and using high energy, and then specifically this nuclear imaging where we have these unstable nuclei. We've talked about those for a couple of chapters now. So what does that mean? We're going to look at some actual chemical reactions now to say, what does this mean that it's unstable? Okay, so we're focusing on nuclear imaging. And specifically that was all these things here where you inject a tracer into a patient. So I'm going to draw you an excellent little patient here just so we can keep this scenario in mind. So we have a patient and we have a syringe that we put an unstable isotope into. So something that's got a nucleus that's unstable. And that is called a radioisotope or a tracer. Okay, once we inject that into the person, now the person is going to be filled with that radioisotope. And the best part about that in terms of imaging is this tracer gives off radiation, right? And so now my patient is giving off radiation and we are able to visualize what's happening inside of them. So when we talk about radiation, we're talking about energy. And when we talk about nuclear reactions, they're giving off energy. So let's first look over here at some of these triangles to see perspective on what's happening at the atom level in some different ways. So what you might see on the door of a nuclear imaging area is the little radiation symbol, okay? There's nothing you can see, so they have to put a sign up. So there's nothing to see. You can see impacts afterwards, or if you have too much radiation, you can see issues, but there's nothing to see. If I consider these reactions at a particle level, here's what's happening, okay? So remember, this is just a single atom. So this could be a single atom that then is unstable and turns into a very similar atom, okay? So what I would start with, this is radon, and we'll see it in a moment here, is my unstable isotope, okay? And then it becomes more stable by giving off a small part of itself, and now it is stable. So before it's unstable, and then afterwards it's going to be more stable. It may still be radioactive depending on the substance, but most of the time it's not going to be radioactive anymore when we look in medicine at least. So unstable and more stable. That's the particle picture. If I write that as what we call a chemical reaction, then I can see that I start with radon here, Rn, and I could find that on the periodic table. And that radon gives off what's called an alpha particle. That's this thing here. And then we have our more stable product here. So this alpha particle, you have a handy reference on your last page of your lecture slides for this chapter. There's 4 different types of radiation that can be given off in these nuclear reactions: alpha, beta, positrons, and gamma. And so we happen to be looking at the alpha particles here, but this is a good reference sheet to have handy as you're working on these. All right, so we have our patient gets injected. Here's what they actually got injected with, was the purple unstable, and now that's giving off this radiation. And one other thing to look at here is there's this T1/2, which we'll see in the next bit of lecturing, but T1/2 is the half-life, and this is going to be how long it takes half of that unstable substance to become more stable. So after 3.8 days, half of this is more stable. All right, so if we are going to look at these nuclear reactions and take words and turn them into this sort of symbolic representation, see if we can do that. All right, so radon-222. So I need to go to my periodic table, which I need to go find. All right, you've got it from chapter 2. Radon-222, this is going to be, these are the masses here. And so you can roughly start to find your way around the table. The heavy masses are at the bottom, right? Here's 222, and here is radon. So I want to use that box on the table to tell me what the number of protons are, the atomic number. And I'm going to write my symbols upside down when I do these nuclear reactions. In other words, on the table, the mass is at the bottom, but here I'm going to put the 222 on top, and then I'm going to put that 86, which remember was my atomic number, and is always going to be linked with that radon. But the 86 is going to go down at the bottom, and that's from this box on the table here, okay? So radon decays. Decay is like when something falls apart, right? You go into the woods and something's decaying, or your fence at home is decaying. it's falling apart, it's crumbling. So decays is going to be represented with this arrow. I've got my before and then my after, okay? It decays and emits an alpha particle. So alpha particle, you could go to that last page of your notes if you wanted to refer to that and see what an alpha particle is, all right? And let's just write it in here. For our alpha particle, it's going to be helium with 2 protons and a mass of 4, or you could also write that as alpha, 2 protons, mass of 4. Either one of those means the same thing, okay? So radon decays and emits an alpha particle. So I'm going to write 2 protons, helium, total mass of 4. So that's my alpha particle. That's also my energy, right? My radiation. And so then your task on problems like this is to figure out what else goes here, okay? And so this is going to be a simple A is equal to B plus C. These have to add up to give me that. These two on this side have to add up to give me the radon. So if I look at the numbers here, if I have 86 protons on the reactant side, the left side, I need to have 86 protons on this side. And I have 2 plus what? 2 plus what will give me 86. So that's going to be 84, right? So I know that whatever I have, I've got 84 protons here. And then top numbers, I can think of this as an equal sign, right? So 222 mass is equal to 4 plus what? I have to conserve my mass. So 4 plus 218 will give me 222, all right? Now from there, I need to know, well, what element is this? So grab your periodic table, and 84 is your magic number. So find 84 on here as the atomic number. Here is 84, and it's polonium. So the symbol that I write in to finish this reaction is PO. Look what I just did. Radon decays and emits alpha particle and this polonium. And if you see, that's exactly the same reaction we had here. Radon emits an alpha particle and a polonium. This is going to be more stable. This was not stable to start with. So my radon, just to add one more color here, my radon was my unstable isotope, right? And now it has become more stable. So that is writing a nuclear reaction without getting all of the destructive radiation actually coming at you. Let's try that for a couple of other types of nuclear reactions, and then I'll leave you some space to practice as well. Radon is a dangerous gas that seeps up out of the ground, and it's very dense. So you find it in basements especially, or crawl spaces. And if you breathe it in, it's too heavy to breathe out. And so after smoking, this inhalation of this gas is actually the second leading cause of lung cancer. So these radioisotopes show up in places in the real world once you know to start looking for them. So let's mimic our same pattern. That's what we do with our problems, is just mimic what you did before for the next one. So F18, so I know I have F. I know this is going to be my mass, which goes on top. Okay, this is my radioisotope that I'm drawing out here. Look at your periodic table, find fluorine, and that tells you that the atomic number is 9, right? So 9, and anytime I have fluorine, it's always going to be 9. Okay, something else. This is F18. Notice on the table the mass is 19. This is not what we're going to use medically. So any number that they give you for a mass in a problem, that's what you want to use. Don't go use the mass on the periodic table. So F18 decays. That's my decay, and emits a positron. All right, positron is something new. If you go and look here, positron has this Greek beta and then a +1 and a 0. In other words, it has a +1 charge and no mass, or very little mass. It's an electron, but a positive electron, which kind of blows my mind. But what I need to know is go look for that positron, okay, and be able to copy down that bit of energy. So beta +1 and a 0, okay? There's my radiation that I'm going to harness for my nuclear imaging. And now I get to kind of do the puzzle here to solve what's going to go here. So remember, this is equals. Okay, let's start at the top. 18 equals 0 plus what? That's kind of your x over here, right? Well, that's easy. 18 plus 0 equals 18. And then here at the bottom, x plus 1 equals 9. So that's going to be 8 plus 1 equals 9, correct? Now I need to know what element do I have. So here the 84 helped me get to the polonium. If I can look at element 8, atomic number, right? 8 is oxygen. So that 8 tells me that I'm going to write oxygen here. So fluorine decays, emits a positron, and I also get this more stable oxygen. All right, let's do 2 more of these together. TC99M, so TC99M, that M stands for metastable, which is somewhat stable. Technetium is the most common used isotope for medical imaging. 99, I'm going to find it right here at 43. So 43 decays and emits a gamma ray. If you look up gamma rays, they are this lowercase Greek gamma, and they have no mass and no charge. So all zeros. Sometimes you won't even see numbers written, okay? Which means the math is going to be really easy here. So technetium, oh, I just kind of got ahead of myself there, because I know the answer. I don't know what's there yet, but I have something plus 0 equals 43. So that's going to be 43. Something plus 0 equals 99. If I go look up element 43, well, element 43 is still technetium, right? The only difference here, and this is my energy that I'm getting, the only difference here with the technetium is here there was an M, meaning it was metastable, and here basically the nucleus has stayed the same, it's just shifted positions, and so now it's more stable. And in the process we get this gamma ray, and the gamma ray is what I'm getting here when I see the orange. I just want that bit of energy spit out as it becomes more stable. All right, one more, carbon 14. Remember, this is carbon dating, so carbon mass of 14, atomic number of 6, if I look on the periodic table, decays and emits a beta particle. Beta particle is an electron, so it's got a negative charge and almost no mass. All right, so I've got that beta particle. Now we have to fill in our x's over here. So 14 equals 0 plus what? 14, right? 14 plus 0 equals 14. And then down here, what minus 1 gives me 6? This one you got to think about a little bit. What minus 1 equals 6? This is going to be 7 minus 1 equals 6, yeah? So take that 7, find element 7 on the table. It's the atomic number, nitrogen. And so from that 7, I can get to nitrogen. So when carbon 14 decays and emits a beta particle, we get a more stable nitrogen nucleus. All right, so that's how we write nuclear reactions. That is what's happening that gives off this orange that we've been coloring, this high energy. I've left you a few to practice here, and another illustration of this fluorine one that we saw here as well. So go ahead and practice those, redo these, and we will work on these together in class also.